4 engines, 1 gearbox, and a driver sitting in the middle of it all, trying to keep the whole thing from tearing itself apart. That was the promise of Britain's boldest post-war locomotive, and also the problem because on paper it looked like genius, but in real life it sounded like a war breaking out under the floor and ended more often in oil, smoke, and silence than anything resembling progress. Right after World War II, Britain wasn't choosing between good and bad ideas. It was choosing between what was possible and what was affordable. And those were two very different things. When copper was being rationed like food and the railways had just been nationalized in 1947 with balance sheets bleeding red ink, because the London Metal Exchange had copper sitting at around 210 pounds per ton if you could even secure it, and most of it was tied up in post-war debt repayments, meaning British railways were scraping by on roughly 5% of the national allocation, which barely covered signals and maintenance, let alone the 20 to 30 tons of copper needed for a single diesel-electric locomotive's generator and traction motors. And when you multiply that by a fleet of 100 locomotives, you are suddenly staring at a number that could swallow nearly a third of the country's available supply. So the Board of Trade did the math and immediately backed away from diesel-electric designs, not because they were bad, but because they were simply too expensive in materials alone. At the same time, the physical railway network itself was quietly dictating the limits of ambition, because many of Britain's bridges were Victorian-era structures never designed for the axle loads of heavy American-style diesels, forcing engineers to cap locomotives at about 21.5 tons per axle. And while steam engines could distribute their mass across multiple wheels, diesel-electrics concentrated weight in the worst possible places due to their motors and generators, which meant you either redesigned half the railway infrastructure at enormous cost, or you found a way to build something lighter. And that is exactly where mechanical transmission stepped in. Because instead of tons of copper and massive electrical systems, it relied mostly on steel, oil, and gearwork, using less than a ton of copper per locomotive, which suddenly made it not just an engineering choice, but a national policy. By 1949, internal memos were already pushing mechanical transmission as the preferred route under constraints of weight and material scarcity, with a target locomotive weight of roughly 116 tons total. And the logic sounded clean and convincing in a boardroom. Because if you could somehow combine the output of multiple smaller engines into a single drive shaft using gears instead of generators, you could solve both the copper shortage and the axle load problem at the same time. And that somehow is exactly where things started to get dangerously ambitious, because nobody had actually built a system capable of doing that reliably at this scale. Yet the committees approved it anyway, because the alternative meant either spending money Britain didn't have or delaying modernization entirely. That is the environment Leonard Fell walked into, an RAF colonel with an aerospace mindset where redundancy meant survival. Because in aircraft design, you don't rely on one engine when failure is always a possibility. You use multiple engines so that if one dies mid-flight, the system keeps going. And Fell applied that exact thinking to railways, asking a question that sounded simple but carried enormous consequences, which was why rely on one large diesel when you could use 4 smaller ones, each capable of stepping in if another faltered. And from that moment, the blueprint of the Fell locomotive began to take shape, not as a conventional machine, but as a rolling experiment in controlled complexity. At its core were 4 Paxman 12 YJV 12 engines, each producing about 500 horsepower, giving a combined output of 2,000 horsepower, with each engine built around a 7-inch bore and nearly 8-inch stroke, arranged in pairs at either end of the locomotive like synchronized rowers in a racing shell. And if they stayed perfectly in time, the system could deliver impressive performance. But if even one engine drifted out of sync, the imbalance didn't just reduce efficiency, it sent violent shockwaves through the drivetrain. And Fell didn't stop there, because to extract maximum performance, he added two auxiliary AEC diesel engines, each producing around 150 horsepower, whose sole job was to drive roots blowers that forced air into the main engines, bringing the total to 6 engines working in tandem, all feeding into a single mechanical system. The connection between those engines and the wheels relied on fluid couplings, which acted as a buffer to prevent direct mechanical shock, using a system where one rotating impeller pushed oil onto a turbine connected to the drivetrain, allowing torque transfer without solid contact. And crucially, these couplings used adjustable scoop tubes that controlled how much oil entered the chamber, meaning at low speeds, you could allow significant slip, sometimes up to 20%, letting the engines spin freely while the wheels gradually caught up. And as speed increased, the system would reduce slip to as little as 1 or 2%, theoretically delivering almost full power to the rails, with only about 1 to 4% loss, which sounds efficient on paper, but depended heavily on precise control, because too much oil too quickly could cause violent engagement, while too little meant the locomotive wouldn't move at all. All of that power then converged into what can only be described as one of the most complicated gearboxes ever fitted to a locomotive, using multiple stacked differentials to combine the output of 4 engines into a single shaft, with each stage attempting to balance torque between inputs. But unlike a car differential that manages 2 wheels, this system was handling 4 independent power sources, meaning any mismatch in engine speed created internal stress, vibration, and gear conflict. And mechanics quickly realized that this gearbox wasn't just a component, it was the entire risk of the project concentrated into one dense, overworked assembly. Operating the Fell wasn't driving in the traditional sense. It was more like conducting an orchestra where every instrument could explode if mistimed, because the startup sequence required first bringing the auxiliary engines online to power the blowers, then starting engine 1, carefully monitoring oil pressure, manifold air, and temperature, then gradually engaging the fluid coupling using the scoop control, allowing the train to creep forward at around 6 miles per hour before introducing engine 2, matching revs precisely to avoid shock loads, and then at roughly 17 miles per hour bringing in engine 3, followed by engine 4 at around 24 miles per hour, with each step increasing not just power but vibration, noise, and risk, until all 4 engines were engaged and the locomotive was producing its full 2,000 horsepower. At that point, the experience inside the cab was less like operating a train and more like sitting inside a mechanical storm, with noise levels often compared to multiple aircraft engines running simultaneously, vibrations strong enough to loosen bolts and numb the crew's feet, and a constant awareness that any mistake in timing or mechanical failure could cascade into catastrophic damage, which is exactly what eventually happened, because under these conditions, even a single failed bolt inside the gearbox could turn into a chain reaction. And when one did fail, it didn't just stop the system, it shattered it, sending metal fragments through spinning gears, seizing the differential, and effectively destroying the transmission in seconds. Recovering from such a failure wasn't quick or simple, because the locomotive, weighing around 116 tons, had to be carefully towed at low speed to avoid further damage, often taking an entire day to move short distances while cleanup crews dealt with oil spills on the tracks. And once it reached Derby Works, the teardown revealed extensive internal destruction, with repair costs for the gearbox alone reaching around 1,200 pounds, which at the time was more than a skilled worker's annual wage, and every repair required custom machining, since no spare parts existed for a one-off experimental design. Despite repeated efforts to fix and refine the system, the underlying complexity never went away. And by 1958, with diesel-electric technology improving and copper shortages easing, the economic argument for the Fell locomotive had completely collapsed, because a brand new diesel-electric could be purchased for under 30,000 pounds with far greater reliability, making continued investment in a fragile experimental machine increasingly difficult to justify. And then, in September 1958, the final blow came not from the gearbox or engines, but from a fire in the steam heating boiler, which rapidly spread through the rear of the locomotive, gutting the structure and leaving it beyond practical repair. Within days, the decision was made to scrap the locomotive, with official records simply marking it as withdrawn and dismantled, ending one of the most ambitious and troubled experiments in railway history. Not with a dramatic final run, but with a quiet administrative conclusion that reflected the reality of its performance. Because for all its innovation and raw power, the Fell Locomotive ultimately proved that complexity without reliability is a dead end, no matter how clever the idea looks on paper. What makes this story still relevant today is not just the machine itself, but the lesson behind it. Because in a world increasingly driven by layered systems, whether mechanical or digital, the temptation to solve problems with more components, more redundancy, and more interconnection is stronger than ever. Yet the Fell stands as a reminder that every added layer introduces new points of failure, and sometimes the smartest solution is not the most complex one, but the one that does the job with the least opportunity to break. So now I'm curious, if you were in that cab, feeling the floor shake under 4 engines and knowing one mistake could destroy the entire machine, would you trust it to pull you across the country? Or would you take something quieter, simpler, and proven? And if you enjoy deep dives into engineering stories like this, where ambition meets reality, make sure to subscribe and let me know what you want to see next.